As a data analyst or data scientist, you will have heard how important statistics is in your journey. Some will recommend you start with statistics, while others will say, oh, after learning the basic tools, then go ahead and start learning statistics. Most of the content are how they actually approach statistics from the technical and theoretical part. You just start cramming formulas and you are finding it difficult to see how it relates to the career you are building. In this course, I'm going to be walking you through this statistical test but in a very relatable manner using business scenario. We're going to cite a business use case, go through the processes of analyzing statistically, use a user-friendly tool to analyze the data and make conclusions. So the likes of one sample test, chi-square test, analysis of variance, correlation, regression. These and many more are what we'll be dealing with in this course. I can't wait to share all this with you. By the way, I'm a trained statistician, I'm a Microsoft certified trainer, and even an ex-Microsoft most valuable professional. So you definitely get the best from this course. See you! In this video, I'm going to introduce you to statistics, tell you about variables and data, tell a data story, and also share some common terms that you need to understand what you'll be doing or how you can use statistics as a data analyst or data scientist. This is foundational, but it's very important to advance your skill, especially as you proceed in this course. So let's start the class. These are the things you'll be learning in this course. Beyond the basis of statistics, you learn about descriptive statistics, inferential statistics, and tons of practical. Okay, so let's talk about statistics. Statistics is the science of collecting, organizing, summarizing, analyzing, and making inferences from data. So, as you can see, data is the foundation and data remains the oil. Very soon, I'm going to share with you exactly the significance of statistics so that you get to understand why statistics. We've talked about what statistics is, but why statistics? So before that, let's consider this data story. I call it a game of insight. This story was, I read it from Warren Dean. During World War II, fighter planes will come back from battle with bullet holes, as you can see on the screen here. So the Allies found the areas that were most commonly hit by enemy fire. They sought to strengthen the most commonly damaged parts of the planes to reduce the number that was shot down. Ideally, that's how people often interpret this. I might ask you, if I may ask you, what decision will you make from this data? Okay, then let's move on and see how this whole story changed. Then a mathematician, Abraham Ward by name, pointed out that perhaps there was another way to look at the data. Perhaps the reason certain areas of the planes weren't covered in bullet holes was that planes that were shot in those areas did not return. This insight led to the armor being reinforced on the part of the plane where there were no bullet holes. Do you see that? That's how powerful statistics is and insight is. And they only have access to one. There's so many reasons, many insights to pick up from here. But one of the key things is unspoken data. Data that actually speaking, but you can't see them. But they are speaking. What you see at the outside is the holes. But the one that are also speaking louder are even the one underneath, the places where it is not it. Okay, I want you to see the beauty of how statistics can help you win in your career, win as in a business, and all those kind of things. That is the scenario here. All right, as we move on here, there are three categories of statistics. Come to think of it, you want to understand statistics for your own career, as a data analyst, as a data scientist, because you might not have all this background, so just want to understand it, and this is why I'm bringing them to you in easy to digest manner. First, we have descriptive statistics. This is what you often do today: build dashboard and report, analyze data, build charts, and all those things. So this includes collecting, organizing, summarizing, and presenting data. That's what descriptive statistics is all about. But inferential statistics includes making inferences, hypothesis testing, determining relationship, making predictions. That is where we have inferential statistics. And soon you start to understand why and what the differences are. And the last part is Bayesian. So it's a very modern and new category. Yeah, it's not totally new, but it's not common. Bayesian statistics is a branch of statistics that is based on Bayes' theorem. So I'm not going to bore you with that yet. But what this type of statistics actually does is it provides a way of you combining probability plus your prior knowledge. So it's not totally probabilistic. You have prior knowledge about something, so let's bring your knowledge into it and not subject everything to probability. And that's why some of them call it subjective statistics, because it's subjective to opinion and not just probability. Welcome. In this video, we talk about data versus variable, and you understand the statistical scale of measurement. Just like when you go to the hospital, you get tested, just before they can diagnose what is wrong with you in some instances. That's how it is for statistician or data analyst or data scientist that want to use data to solve problems. When you see data, you must be able to quickly diagnose it to understand, what kind of test can I perform with this kind of data, or what data will I need to address a business challenge. And that is why scale of measurement is fundamental. Okay. So let's look at data versus variable. What is data? What is variable? First, look at what I have on my screen here. There is name, and you can see all the names here. Variable now is the name. So variable is a container and data is the content. Let's put it that way. Variable is the heading, and under that heading called name, you can now see some data inside it, which is the data. The variable is the container. Let's use another one to share this, to explain this. Age. Age here, the word age is the container. That is the variable. The values under it is the data itself. And I hope this sort of help you to understand what variable is and what data is. Then let's look at the different measurement levels. There are two major categories of data today. We have qualitative, which are categorical, and we have quantitative, which are continuous. Qualitative, categorical data are also further divided into two. We have nominal and ordinal. If you understand these bases, anytime we are talking about statistical tests or you want to analyze data, this will help you to understand what is possible and what is not. Look at nominal, which is the list of all the entire data level. Nominal are just data for categories. You use nominal data to separate or label information. For example, car brands, Toyota, Ford, except to provide additional context, there is really nothing different. They are car brands, and it's just a label to help you separate one car from the other manufacturer. Gender, if that male or female, it's just to label people, to help you understand their gender. Seasons, except to start putting additional context, it's just to segment and label different faces, in a year. Ethnicity, party affiliation, the state you are living in, and why it's different from other states. The names are labels. So nominal data are the list. There's little you can do with them than just to calculate some frequency analysis and all the rest, and percentage contribution. Except to add additional variable to them, you might not be able to do that much analysis, just to descriptive and show you what is happening there. Then we have the next level, which is ordinal. Ordinal data is advanced than nominal, so it's categorical, but it now have additional value, which is order. Here, rating. Are you sad? Are you indifferent? Are you happy? It's different. And if you're interested in happy, someone who is happy is more higher than someone who is not. And then we also have position. First, second, third. They are labels, they are categories. But first is first because there is order to it. You cannot say it's not. No, first is first. Second is next to first. And second is still improved and better than third, depending on the context we are considering now. So these are categorical data, but they have order. And we also have corporate seniority level. You are a manager, you are a CEO, you are a junior. All those things are levels, they are categories, but they have order. Age group, the higher it is, the older they have order. You can't just put them anyhow. So that is the difference between ordinal and nominal. Then let's go to quantitative, which are data that you can actually measure or count. That's quantitative. The first one are data that are categorical. So the other one is quantitative. They are numbers, that you can either measure or count them. Let's start with interval. Interval is advanced than the first two that we talked about because they are now numbers. You can further break them down by categorizing them. And one example here is temperature. Temperature in degrees Celsius and temperature in degree Fahrenheit. What is different here is that interval does not have absolute zero. What do we mean by that? Whenever it is zero, does not mean it is zero. If a temperature is 0 degrees Celsius, doesn't mean that there is no temperature. It only means that it's cold. If it is negative, it's become to cold, but freezing point is 0. You understand now. So at 0 degrees Celsius does not mean there's no temperature. It just shows that it is very cold. So there's no absolute zero at interval level. So interval is numbers like ratio, but there's no absolute zero. And when you move to ratio, you can easily tell there's absolute zero. As you can see here, number of objects, you can count them, there are 4. If there is nothing there, you know there's 0. And 0 means it's 0. We have distance, that, for example, distance in kilometer or mile. If I ask you today, how many steps have you taken today? If you've not taken any step, 0 is 0. It's not like, oh, 0 does not mean you've not taken any step. It means you've not taken any step. So there's absolute 0 in ratio, and that makes it possible to do a lot of analysis and tests with that kind of data. We also have time. How many hours did you spend reading yesterday? If it is 0, it means you did not read at all. So you can't say because I spent 0 hours reading yesterday does not mean that I did not read. No, you did not read. If you spend 0 hours reading, or 0 minutes reading, then you did not read. All right. So this is where we're stopping for scale of measurement. As you can see, just about variable and data and the different measurement level, which are 4: nominal, ordinal, interval, ratio. In our next couple of videos, we'll be getting familiar with this, the way we use these terms, the way we run them, use them in analysis, and the host of others. All right. So see you. In this video, we're going to get to know or get familiar with some statistics jargons, which are just keywords or terms, that we use in statistics. There are many, but I'm only picking those that will be useful for you to understand and have a good foundation with what exactly statistics is and all those tests that we'll be carrying out in this course. So first is data. It all starts from there. Statistics is about data. So data are raw facts. They are collected from variables used to describe an event. As you can, don't forget, in the last video we talked about variable and data. So data are stored under variable because variable is the container and data is the information or whatsoever, or data is the content inside a variable. So these are the values that the variable describing an event can take. Age is the variable that is showing you the age of people. Then the value under that age is the data. Okay, good. So let's move to the next one. Variable. Simply put, variable is a container that can assume several values. If values are determined by chance, it is called random variables. So some outcome can actually be determined by chance. And in that case, whatsoever you store inside that kind of variable is called random data. But of course, the variable itself is called random variables. Let's talk about population. Population consists of all the data that have been studied in its totality. Nigeria population meaning everybody, all the numbers, not one less, not one more, everybody. Cohort in a class is everybody. There are so many things to describe population, right? And then we move to parameter. Anytime you are studying population, for example, students in a particular class, maybe 100 level computer science students in a particular university, you know that this is the population of that student in that course in that university, because that is your population of study. So when you take data about these people, all of them, and you run some analysis on them, every value you are reporting, they are called parameter. So you are calculating your mean, your median, your mode, but because you are calculating them from a population data, that the data is all the population, then those things are being referred to as parameter. So this is a fact or description about the population. If you calculate mean, median, mode, variance, etc., and data uses the entire population, then these values are parameters. That's how easy to comprehend what parameter is and how it's related to population. Population is everything, and when you use everything to run your analysis, then you are calculating parameter. Then let's move to sample. It's a subset of a population. You agree with me? It's easy to comprehend, and there are so many reasons why you cannot take the population. Number one, it will be very costly. Nigeria, for example, for calculating census in all countries, if you want to carry out census, it's not cheap. It's not affordable. It's not cheap. So company or countries don't run census every time. They often run it every 10 years. And in recent times, it could be even a 20 or 30 years interval. All they just have to do is to do some extrapolation every year to predict what the numbers might be and not run it every year. So it could be cost intensive, resource intensive. Some scenario, it is destructive. If you truly want to take every population in all your tests. For example, if you are, maybe you are cooking soup, and in that soup you want to test if the soup is delicious. Will you consume everything? If you are using the entire population, if you consume everything, it's destructive. You have finished the whole soup. in the name of testing and because you want to test the population. So in that scenario, you cannot test the population. You have to take a sample from it and then determine if the soup is delicious or not from that sample. If you are manufacturing, maybe matches, for example, if you have to strike every stick from that matchstick to be able to test if they are working or not, then you've destroyed everything at the end. In that scenario, you have to take few samples and make conclusion based on that. If you are buying something in the market in the local area, maybe you are buying garri cassava flour, in the market, you don't consume everything in the bowl before you know if it is delicious to your taste or not. You take a sample, you taste it, and you conclude, I like this one or not. So that is how sample work in day-to-day activity. Sample is a subset of a population, and so many reasons why it is the way we live our life is on sample, because in some cases it is impractical to get the whole population, or it's destructive if you want to use the entire population for whatsoever you are doing. And you can get statistic. Yeah, that's where we are going to now. So this is a fact. So this is not the statistics as a course now. This is statistics as a term under statistics. So this is a fact or description about the sample. So when you use the sample when you take sample and you then run analysis, everything you calculate, your mean, median, mode, variance, all those things, as long as you use the sample to calculate those things, they are called statistics. And you can now guess, wow, so this is what statistics is all about. Yes, we live our life by samples. Everything we do today is actually samples. Hardly will you be able to assess the entire population, and that is why statistics is very important. So now everything you are working with is sample data, and that's where statistics is having its relevance. If you have all the population and you can assess them easily and you can do everything with them, I'm not so sure statistics will have value. But the fact that you have sample, you don't have access to the entire population, and you can work with this sample to make a significant contribution. Oh, I want to understand how to do that, because there are many scenarios for this. Wow, this is amazing, right? So I just want you to go ahead, like, subscribe, and share in case you're enjoying this. Thank you very much, and in the next video, we're going to take this further. In this course, we'll be using the IBM SPSS software. SPSS means Statistical Packages for Social Sciences. It's not about the tool, it's just that it's easy to use for me to demonstrate and actually test these different statistical tests. We are not after the formulas and the technical jargons, it's just how do we carry out tests and how do we address business problems and challenges with this test. So you have to visit on your browser ibm.com/SPSS. I'm using a trial version, and you click try SPSS statistics. Just for 30 days, you'll be able to try this. You need to register for IBM account, or if you have one, you click on login. And I already have one, so I just need to log in. I have successfully logged in, and I can see all that I have access to. This is it. You can then click on download to download the trial. I have downloaded mine, and I'll be using it to carry out the statistical test that we need in this course. Alright, so for course resources, a folder has been provided in this course where you can see all the data sets that we'll be using. So you don't have to bother about data set, yours is understanding the business problem, and now we are using data and SPSS to solve that problem, as a tool. So the data sets are here in the folder. You can check the course resource section in this course. You'll be able to do that. You'll be able to see them. If you are watching this on YouTube, of course, check the video description. You see the link that takes you to where you can download all this data for your use. Thank you. We have briefly described or talk about descriptive statistics, which we will soon see in practice. Let's talk about the inferential part of statistics. From the word inferential, it simply means making inference. Because we don't always have access to population, we have access to statistics. And you want to make conclusion, everything you do with statistics, you end up making inferences about population. So this aspect of statistics focus on how you should handle and work with statistics, which is sample now, to be able to make the accurate inference about the population. Just as doctors test patients, we test data to be sure they are fit for purpose and if a claim about it can stand or not. That is the strength of this course. We're going to be taking through those business use case scenario, and we will use statistics to test and make conclusion. This way your mind will be so open and you understand how statistics is being used as a data analyst or data scientist to answer business questions. We are testing whatsoever result we get when we use sample for our activity, and we want to make conclusion about the population. So we then set up hypothesis. So hypothesis testing is a very interesting topic in statistics. You will always have to consider it. I use this with all my activities in statistics. Even in business today, I set hypothesis but not written down in my head and go ahead to test it with the data. So a statistical hypothesis is an opinion about population parameters. This opinion may be true or false. Don't forget, opinion about parameter meaning is about population, because we don't have access to the population. We are working with sample and you want to make inference, make conclusion from the sample about the population. Then you need to test and be sure that thing is saying the right thing. And we have two hypotheses that is often set. First is null hypothesis and the second is alternative hypothesis. For null hypothesis, this is a hypothesis of no difference. It's just like the status quo. This thing is this. No, it's fine like that. It simply states that there is no difference between a parameter or parameters. I'm referring to a population now, and a specific value, which could be a sample value or something. So null hypothesis testing is telling you that even though you are working with sample, I'm comparing this with population, and if your test is valid, then you can make conclusion that okay, this thing is representative of the population. Otherwise, don't make that generalized conclusion. So it is the status quo. That's how I call it. Moving on to alternative hypothesis, which of course you can guess is the counterpart of null hypothesis. So this is most of the time the researcher's hypothesis, what you are interested in. This is the challenging the status quo. It states that there is precise difference between a parameter or parameters and a specific value. So null is saying there's no difference. Alternative is claiming that there's a difference. So you then need to go ahead and test. Based on the result of the hypothesis, you can make your conclusion. All right, it's getting interesting. Null hypothesis. Let's talk about this. When making a conclusion, we do not accept a null hypothesis. Well, you can always be interpreted that way. People often interpret, but ideally, you don't accept. Why? Because the null hypothesis is accepted to be the status quo in the first place, until we prove otherwise. So it is either we reject the null hypothesis or we do not reject the null hypothesis, because it's just making a claim already. And you just want to reject it, or not like accept. It's not asking you to accept. This is how it is. You have to prove otherwise using your alternative hypothesis. So you're just trying to help you to be statistical minded. You can say, oh, we reject it, we do not reject it, but it's ideal to say we reject or do not reject. While you are rejecting or not rejecting, you are making some error, or you are getting some decision right. As a data scientist, this might look familiar, but I'm not putting it in the way you would like to see it. It's called decision matrix. So this is exactly how statistics is being extrapolated to the result of your model building when you're evaluating the performance of the model. So first, null hypothesis. Look at this table. The top at the header, the side is also another label. First one here is null hypothesis is true, is a matrix. To the right, null hypothesis is false. At my left, reject null hypothesis, that's the decision you are making now. Under it, you have do not reject null hypothesis. So let's look at the intercept of this matrix. When null hypothesis is true and you reject the null hypothesis, you are making an error. It's true, you should not reject it. So that is called type 1 error. When the null hypothesis is true, but you are rejecting it, it's type 1 error. The other one is when the null hypothesis is false and you reject the null hypothesis. Oh, you are making a correct decision here. So that is good. Under it here, we see when the null hypothesis is true and you do not reject the null hypothesis. Oh, that's good decision. That's correct decision. And the last one here is when the null hypothesis is false but you do not reject it. So that is type 2 error. So you can see the errors here. That is decision matrix. If you understand this now, so this is how it's come about. It is also from statistics. As we wrap up this particular video, let me just share with you some basic steps you carried out when performing hypothesis testing, because that's what we'll be doing going forward. In the next couple of videos, we'll go ahead and start testing one by one. So first thing to do is to state the null hypothesis. What is your null hypothesis? What is your alternative hypothesis, which is the opposite of the null hypothesis now? State the formula for test statistic and compute its value. So in this case, we're not going to state formula because we're not using hand to do anything here. We're using system to run it. I'm going to be using statistical package for social sciences, which is IBM SPSS, to do this. My choice of it is because I just want something really illustrative for you to understand statistics and not about the tools. It's about understanding statistics and not about the choice of tools you are using. And once you are done calculating and doing you get your result, you're able to state the decision rule for rejecting the null hypothesis for a given level of significance. And after you now compare the result with the decision rule, you can then make a conclusion in the context of the information given in the problem. You don't just make decision and just generalize like that. You can take some poll today, but that poll might not even be representative of the population. So it's good to be mindful of how you make conclusion after carrying out statistical tests. Okay, don't forget, if you like this and you're enjoying it, please do like and subscribe. And if you are watching this right now on Udemy, please do recommend your colleagues and friends, and I really appreciate that. Thank you. These use cases, the business samples that we cited there, were actually gotten from Lied Statistics team. And when I started writing this manual, I literally wrote to them and I got their express permission that they are happy and they would like me to use these things in in my whatever I'm working on, in my research or in my document or manual that I'm building and putting together, including the usage right here. So I just want to mention this so that you are aware. And good. Chi-square test of independence is one of the basic yet powerful statistical tests that you can apply and use in your day-to-day activity. And let's get to know more about this test. Introduction. The chi-square test for independence, also called Pearson's chi-square test or the chi-square test of association, is used to discover if there is a relationship between two categorical variables. Wow. Now we are referencing categorical variables. You can see the relevance now. You might have to jump back to the video where I shared what exactly categorical variables are. Okay, so chi-square test of independence is only applicable to categorical variables. This is the first thing you should take out as we proceed now. For each and all of these statistical tests, there is always assumptions. There are assumptions that you need to meet before you can carry out those tests. So for a chi-square, test of independence, what are the assumptions that must be met before you can say that, I can use this test for this kind of data or business question? First, why this? When you choose to analyze your data using chi-square test for independence, you need to make sure the data you want to analyze passes two assumptions. You need to do this because it is only appropriate to use a chi-square test for independence if your data passes these two assumptions. If it does not, you cannot use a chi-square test of independence, and that's where many people just get it wrong. They don't check for assumptions. They only just run the test because I think I can use this test, and they make conclusion. So everything is not subjected to statistical practices, and that is why people often make some wrong decisions today. What are the assumptions? Number one, your two variables should be measured at an ordinal or nominal level. This is really interesting because we've talked about ordinal or nominal. You see where they're coming in now. If you want to measure or use the chi-square test of independence, first, the two variables you are comparing here must be measured at either ordinal or nominal level, e.g., they are purely categorical data. And number two, your two variables should consist of two or more categorical or independent groups. Let's see. Independent variables that meet this criterion include gender, where you have two groups, males and females. Those are two options now. You can have ethnicity, e.g., three groups with Hausa, Yoruba, or Igbo. You can have physical activity level that has even 4 groups: sedentary, low, moderate, and high. You can talk about profession that has about 5 groups: surgeon, doctor, nurse, dentist, therapist, and so on. So you understand those groups now. If you have any variable that just have one value, it's not appropriate. So you must have at least 2 onward. Okay, now that we talked about assumptions, let's now look at the business use case that we consider here. A marketer wants to know the relation between the brand of smartphone people use and the brand they would like to use. So she collects data on 150 respondents, resulting in a data set that we're going to use, which is called phone_brands.sav. That is the SPSS data format. Do these data refute the hypothesis that the current smartphone is unrelated to preferred smartphone? This is a good business use case. And we have to set our hypothesis. Don't forget, the null hypothesis here is that current smartphone is unrelated to preferred smartphone. But we are saying no, current smartphone is related to preferred smartphone. We can't continue to argue this, but we need to test. Okay, we collected data. We asked people what smartphone would they like to use, what brand are they using today. So we now want to test between the smartphone they would like to use and the brand they are using today. Now that our hypothesis is set, it is time for us to run the test. So in the next video, we're going to carry out this test with SPSS statistics and then come back and make conclusion based on it. I have IBM SPSS statistics open up right now, and I'm going to locate the data. Don't forget, we have a folder where we have this practice data in case you want to practice alongside. I'm going to click on File, Open, then locate my data in the folder where it is. My data is actually phone_brands.sav. So I'm going to open it up. Let's quickly look at it. What we have here are 3 columns. One is ID, just to number the entire sample that we collected. The first column here is current, which is like current brand of smartphone that you're using today, and the other one is what brand of smartphone would you have preferred to use. Okay, and you can use this button to actually toggle between numbers. Computer understand numbers, so at the back end is this number that will be used for the mathematical calculation. Meanwhile, we can read the data as text here. If I go to the variable view, you can see where the variables are defined. This is the value here. We have the ID, which is just to number them, is taken as a scale. We also have the 2 choices of brand phone. What is the brand of your primary smartphone, what they use today, and what are the values there? We see Samsung, HTC, Apple, and others. Those are the brands being considered in this study. And this is nominal because it's just a category to label them. And we have what brand they will have preferred to use. We also have the same brands here. It's just a cross tabulation to understand what brand we have preferred to use, which one are you using today. And we want to test if they are related in any way. All right, you get that. I'm coming back here to data view. I need to carry out my analysis by going to analyze here and go to descriptive statistics and come down to cross tabulation. When I click on cross tabulation, it's going to show me this that I have right on the screen. What is the brand or smartphone that you use? That is what I'm going to put here in row. The second variable will goes to the column so that I can do a cross tabulation. That is not enough. I have to also select other things I want to do. For example, display cluster bar chart. Show me a bar chart that sort of describe how the relationship is, and I can go to statistics where I can tell exactly what I want to carry it out. I can select chi-square, which is the test we want to perform now. I can also select fill and Cramer's V, which is the a way to calculate correlation. These data are not quantitative, they are categorical. So how can I understand the relationship between them? Instead of just selecting correlations, I can use fill and Cramer's V to do just this. And I'm be okay with this without something complicated. Click continue, and you might want to select the cells in case you want to. So I need observed and expected value, or calculate percentage for row, column, and all those numbers in case you are interested there. For example, let's say row, column, and total. Calculate percentages for them. And if that is all, click continue, and let's go ahead and click OK. Right now, the test statistic is going to be run and the result is out. And these are the results. We have this big table that just shows us the cross tabulation and the percentage distribution. This is what brand of smartphone you like to have and what are the brand of smartphone you use today. So for Samsung, this is the count. This is the meeting point of using Samsung today, and you like to use Samsung is 27. You are using Samsung today, but you like to use HTC, the 11, and this is the percentage. Using Samsung today, and but you like to use Apple, this is the number. Or you're using Samsung today and you like to use another brand of smartphone not even listed there, these are the numbers. That is what this cross tabulation is all about, and it's just so interesting to look and analyze. And this is the chi-square result, which we'll be talking about soon, and symmetric measure, which is the Field and Cramer, just to show how correlated these numbers and values are to each other. Remember, we chose cluster bar chart, so it ought to plot this for us. You can see Samsung as a smartphone now, and we see likely people who are using Samsung, they would like to use Samsung and are currently using Samsung. That's the highest. When it comes to HTC, they would like to use HTC and they are currently using HTC. That's the highest. They use Apple today and they like to use Apple. That's also the highest. Other phones too. So there seems to be a correlation, but we cannot conclude until we check this table here, chi-square table. To make that conclusion, let's go back to a slide where I can just walk you through the result of the analysis. One of the most important table when it comes to making decision based on the chi-square test is what you can see right there, the chi-square table. And when reading this table, we're interested in the result of the Pearson chi-square rule. We can see here that that symbol that says Pearson, that x and raised to power of 2 means Pearson chi-square value, and the result is 131.206. That is the result. Statistically, a probability value has also been calculated, which is called p-value, and which is equal to 0.000. In many scenarios, it is not that it's 0, it is just that it's 0.00 to several digits, but it's always approximated to 3. And what this means is it is significant. So this tells us that there is a statistically significant association between what is the brand of your primary smartphone and what brand of smartphone you would like to have. And this p-value, when you're making your decision, you often say if p-value is less than 0.05, that is 5% margin of error, meaning you can take more than 5% margin of error. Let's assume no model is perfect, but let's assume you take less than 0.05, which is 5% margin of error. That means you are 95% confidence, those confidence interval. But here p-value is actually 0.000. So we are saying is if the p-value is less than 0.05, which is our expected, researchers' hypothesis significance level. If p-value is less than 0.05, then you can reject the null hypothesis. So let's go there and see that now. Can we make that decision? Can we reject the null hypothesis? Here is the conclusion. Current smartphone is unrelated to preferred smartphone. We reject that hypothesis because we found out from the analysis that is significant. P-value is less than 0.05. It is 0.000, meaning that is way less than 0.05. When we reject the null hypothesis, we then go ahead and accept the alternative hypothesis, which state that current smartphone is related to preferred smartphone. You get? All right. So you can see how we use statistics here to literally make that conclusion, and not just by observing the chart and the graph, which many people do today. Wow, I hope this is amazing. I hope you are learning, and I want you to like and subscribe in case you're watching this on YouTube, or actually share with your colleagues in case you are watching this on Udemy. And don't forget to rate and review this course because I really appreciate it. Thank you. In this video, we're going to talk about one sample t-test. It's also one of those basic and yet powerful test option in statistics. One sample t-test is used to determine whether a sample comes from a population with a specific mean. This population mean is not always known, but is sometimes hypothesized. Let's look at an example. You want to show that a new teaching method for pupils struggling to learn English grammar can improve their grammar skills to the national average. And you could say, oh, last year the national average is maybe 60%, and you now taught them something new this time around, and you assess them and you want to compare, is their scores now significantly higher than the national average, which you know as the last year was maybe 60%. This is where you can really use one sample t-test. Let's talk about the assumptions of one sample t-test. It also has assumptions. So when you choose to analyze your data using a one sample t-test, part of the process involves checking to ensure that the data you want to analyze can actually be analyzed using a one sample t-test. You need to do this because it is only appropriate to use this test if your data passes 4 assumptions that are required for a one sample t-test to give you a very valid result. So let's consider the assumptions one after the other. Assumption number 1 is the independent variable should be measured at interval or ratio level. Now we're talking, we've talked about this before, right? You should check the first part of this video where I explained all this interval, ratio, level, and now it's becoming an assumption. So if you don't understand this, you will need to fall back to that video to get this. Examples of variables that meet this criterion include revision time, is measured in hours, intelligence measures using IQ score, exam performance measured from 0 to 100, weight measured in kilogram, and so on. So it is not categorical at all. It is number that you can measure or count. That's the first assumption. That variable should be that. Number 2, the data are independent, so not correlated at all, which means that there is no relationship between the observations. This is more of a study design, than something you can actually test for. But it is also important that when you are designing the study, you ensure that this is being addressed. Assumption 3, there should be no significant outliers. It's not going to be maybe there's one FICO or one brilliant guy that just score high, and it's that high score that is lifting others. In that scenario, you might not conclude, it might affect the result. Outliers are actually data points within your data that do not follow the usual pattern. They are extremely either high or low than the variation or than the average and variation. Now, let's take for example, in a study of 100 students' IQ scores, where the mean score was 108, that's the expected average, with only a small variation between students. One student had a score of 156, which is very unusual, and may even put up R in the top 1% of IQ scores globally. That's an outlier. When you now calculate the average now might be more than 108, might then be maybe 120 something or 130 something. Can you then conclude that this class is performing well? No, it's just that number that makes it shoot up. So that's assumption 3. Then 4, your dependent variable should be approximately normally distributed. When we talk about the one sample t-test, only requiring approximately normal data because it is quite robust to violations of normality. So if your data is not normal is like saying ceteris paribus. When all things being equal, then we can make this conclusion. So ceteris paribus. So in statistics, we also run on those assumptions. You don't just make conclusion. Those assumptions must be met. But in a situation where the normality is not met, one sample t-test is very robust, can still be accurate, even when this particular assumption is not that met. That's what we mean here. Okay, so let's look at the use case here, and we then run the test. Scientists from Greenpeace, for example, is a fictitious use case now. Scientists from Greenpeace believe that herrings is an animal in the North Sea don't grow as large as they used to. So it's well known that on the average, herrings should weigh 400 grams. That is the population data. The scientist catches and weighs 40 herrings. So they carry one by one and started weighing them 40, resulting in this data set called herring.sav. Can we conclude from this data that the average herring weighs less than 400 grams? We have to put up our hypothesis. Our null hypothesis is that average herring weighs around 400 grams. That's what we expected. But we are trying to test it against a new belief that average herring weighs less than 400 grams. You get it right? So let's go ahead and carry out our test. And from the test, we can then compare the result and make conclusion. Now, do we still believe that an average herring weighs around 400 grams, or they are now significantly weighing lower grams in terms of weight? Let's go ahead and run our test now. It is time for us to run our test, and the first thing we should do is to import our data by going to File, Open, and Data. We already have this data in our example folder, and it is herrings.sav. I'm going to open it up. Because we are interested in one sample t-test, we don't need to have multiple variables. you might want to calculate this for multiple variables, but we only have one data, which is body weight of herring. So let's move to the variable view and see how it's being configured. It is just variable name is here, and we have the description in terms of labels, and it is scale data because it's continuous, and that's one of the assumptions for calculating a one sample t-test. It's not categorical, it's continuous. Okay, then for us to carry out our test, you just go to analyze and you go to compare means and proportions. You will see one sample t-test. I click on it. I should pass the variable that I'm interested in. I've passed it here. What value am I testing against? Is 400. We expect on the average an herring often weigh 400 grams. So let's see if this test is significant or not against it. And I have options here. By default, it's 95% confidence interval. You might want to change it, but we'll keep it as this. So 95% confidence interval, that's 0.05 margin of error. And I'm going to click on continue and click OK right here. The result is simple, right? So if you look at this one sample t-test statistics, it's saying 40 data set was compared. This is the was computed. This is the mean 369. That's less than 40. That's less than 400 grams, right? But we can't conclude if it's significant or not until we check the table. And you can see the standard deviation and the standard error. And the most important table here is the one sample t-test, which compares the result we have on this descriptive table to 400 grams. And we can see all the results here: the test statistics, the degree of freedom, the p-value if it is one side you are interested in. For example, either is less than that number or greater than. The two-sided means it is not equal to 400. So either less than or greater than. If that's what you are interested in, this is the value you get. This is the mean difference between them, 30. It's 30 grams less than the expected. But is this significant or not? We will check that, in the interpretation of the result. But you can guess already what the answer will be. Okay, so let's move ahead and interpret this result now. It's so interesting to see how valuable these statistical tests are. Look at the business scenario we're comparing, and now we have a result. In the last video, we did this analysis and we had a lot of statistics thrown at us to help us to make this decision that we are making right now. A one sample t-test was run to determine whether body weight of herring in grams was different to normal. Historically, it's believed that the body weight of herring should be around 400 grams. Body weight of herring in grams were normally distributed as we assess using Shapiro-Wilks test, and were no outliers. There was no significant number that is so big or so small, too small, that could cause a misinterpretation of our data. We also assess this by inspecting the box plot. The mean, which is the average herring, weighs 369.55 grams. That's what we found, with the standard deviation of 79 grams. Meaning variation we observe within the data. It's 40 herring that we actually weigh, not just one, and we calculated the average. And this average was lower than the normal body weight of herring, which is around 400 grams. 369 grams to 400 grams is significant, because the difference of 30.45 grams. So it was lower than the normal body weight of herring grams. And a statistically significant difference of 30.45 grams with a 95% confidence interval of minus 55, which is what you can see on that table there, minus 55.81 grams to minus 5.09 grams. The statistical test was calculated, and what you should pay attention to is the significant level, which is p-value here, that's sig2 tail. P-value here is 0.02. And for us to make a decision, we're going to reject the null hypothesis if our p-value is less than 0.05. We are using a 95% confidence interval here. And the p-value is 0.02. Is 0.02 less than 0.05? Yes. If that is the case, then we reject the null hypothesis. Looking at the null hypothesis, average herring weighs around 400 grams. We reject it because from all the things we calculated, the average weight is around 360 something grams, 69 grams, which is significantly lower than 400. And we then accept the alternative hypothesis that states that average herring weighs less than 400 grams. I just want you to pay attention to this conclusion that I have here. Although a statistically significant difference was found between body weight of the herring versus the normal body weight of herring that we're expecting, it does not necessarily mean that the difference encountered, which is about 30.45 grams now, is enough to be practically significant in many scenarios. Indeed, the researcher might accept that although the difference is statistically significant and will report this, which is what we are reporting now, the difference is not large enough to be practically significant. So you also consider that sometimes. If it is, maybe it is now 301, compared to 400, well, that is huge. You then have to look at the norm. Is 30 gram difference in average? Is this something that is now significant that we can then conclude that average earning now are totally less than what it used to be before? So the practical significance is also very important. So I would just want to call your attention to this. This is interesting, isn't it? Yes, please do like, subscribe, and share if you're enjoying this. And if you're watching on Udemy, please do rate this course. I would really appreciate it. It gives me encouragement that you're enjoying this and you're finding value in this course, and share with your colleague, or kindly refer this to someone else who wants to understand statistical tests by looking at how it's being carried out and applied in business use cases. Thank you. Let's talk about independent sample t-test. What exactly is it? The independent sample t-test, or independent t-test for short, it compares the means between two unrelated groups on the same continuous dependent variable. So I'm going to explain this to you. So we have categorical variable and we have a single dependent variable. For example, you could use an independent t-test to understand whether first year graduate salaries differ based on gender. So the gender here is unrelated groups, because you have male and female, they are separate gender now, so they are not related. And which is your dependent variable will be first year graduate salary, that's continuous data, while your independent variable will be gender, which has two groups, male and female. It is also important you are familiar with the assumptions. So let's go through the assumptions of independent sample t-test. There are a couple of assumptions, but why assumptions? When you choose to analyze your data using an independent t-test, part of the process involves checking to make sure that the data you want to analyze can actually be analyzed using that independent t-test. You need to do this because it is only appropriate to use an independent t-test if your data passes 6 assumptions that are required for an independent t-test to give you a valid result. And what are the assumptions now? Number 1, your dependent variable should be measured at the interval or ratio level. Don't forget, it should be continuous. Examples of variables that meet this criterion include revision time measured in hours, like anything you can measure or count. You remember we've talked about this at the early part of this course. The second assumption is your independent variable this time around now should consist of 2 categorical independent groups. So if you are using whatsoever you are having as your independent variable should not have more than 2 groups. It's very important. E.g., you have gender, which has male or female. You have another kind of employment status, employed or non or unemployed. It could be loan status, default or non-default. Smoker groups. Are you into smoking? Yes or no. These variables that I've mentioned have only 2 categorical options. Those are the independent variables that are fit for this kind of test. And number 3 is you should have independence of observations, which means that there is no relationship between the observation in each group. They should be independent. If you are comparing for gender, male or female, those who are male cannot say I'm also female. No, they should be separate from each other. If it is employment status, you are saying unemployed and employed, you shouldn't have anybody falling into both categories. They should truly be independent. That's what it means here. And number 4, there should be no significant outliers. If you have any extreme value that can drop the average value or increase the average value, this can have influence on your result and can make it invalid. So you should also try to correct that. Number 5, your dependent variable should be approximately normal. Everything seems to revolve around the assumption of normality, which is like ceteris paribus. Let's assume all things being equal, and you must get to that point where all things are assumed to be equal. One more thing to just know that is that independent sample t-test is actually robust. So violation of this normality assumption might have little impact on it. The result can still be valid. And the last one is there needs to be homogeneity of variances. You can test this assumption using Levene's test and homogeneity of variances. But what exactly is homogeneity of variances? We're going to talk about this later. What is the use case that we consider here? A market wants to know whether women spend the same amount of money on clothes as men. She asked 30 male and 30 female respondents how much, in euros they spend on clothing every month, resulting in this data set that we have clothing underscore expenses. The question here is this: do this data contradict the null hypothesis that men and women spend equal amount of money on clothing? So we can see right there the question is there, and the hypothesis is clear. Null hypothesis is that men and women spend equal amount of money on clothing. The alternative hypothesis is men and women spend unequal amount. This is double-sided. If you go back to this question, it's interested to see if they spend the same amount, not maybe one spend more than the other. So the direction is not about male spend more than female or female spend more than male. Just curious if they spend the same thing or not. So it could be other way. It could be that later men spend more than female women, or women spend more than men. Okay, so we have our hypothesis set. It is time for us to go and run our test. We're going to run this test with our data, and once we're done running the test, we come back and interpret the results of the test. Much more in details now. I bet you're also interested in the result of this particular test. It is independent sample test, and let us see it in action. So the first thing to do is to import your data by going to File, Open, and click on Data. Clothing expense, that's what it is. I click on it and click Open. Right, so we have this here. We have two variables. One is gender, the other is amount spent. And look at gender here. It's been taken as number. Should it be? I'm not sure. If I use this button to toggle, you can see it's moving from 0 to 1. Maybe that's why it's taken as number. We can reconfigure it. And we see amount they spend. Look at the way it's positioned. Look at the way it's been configured here. It is not maybe male and female, and you can then see what they spend under them. It is factored. A column that talks about gender, another column that talks about the value. It is also important if you want to run this kind of test. Let's go to variable view and see how this thing is being configured. So gender, for example, 2 decimal places. I don't need gender in 2 decimal places. It's 0. I can keep it at 0. And this value here, it's 0 for male, 0 for female, 1 for male, which is fine. That's the way it's coded. And this should not be, the measure should be nominal. Why this order should be scale? Because it's amount, which is continuous, or is continuous, is a continuous data. So we've done little configuration that we are okay now with it. And I go back to my data view, and you see it's fine. If I toggle this back 0, 1, which is fine, male and female, and this amount displayed. You navigate to Analyze, compare means and proportion, and you see independent sample t-test. We have to put our categorical variable under grouping variable here. I keep my continuous variable, which is my dependent variable, under test. And when I click back on this group, I need to define the group. It is 0 and 1 and not 1 and 2. Otherwise, it will not understand what I used to code them. So I need to turn this to 0 and 1 and 1 here and click continue. I need to go to options here. And by default it's 95%. You might want to change it, but that's what we are testing. We're actually using 95% confidence interval in this test. And other things you can do is estimate effect size if you need that. I'm fine. The other tests you can carry out, but this is what I'm actually interested in, just to show you how to run this kind of test, and click OK. The result is here. You can run additional multiple tests to test all the assumptions, but here is the actual result you might end up falling on. This is the comparison of the mean for females and for male. Let's take a critical look at this. They are the same number, 30 that was selected. And you can see here females have higher value than male, but we can conclude if this is significantly different because the variation also differ. It's not like all of them are spending high. We see a lot of variances here. Some females actually spend ridiculously low, maybe not ridiculously low, but very low. And some actually spend more than, the variation is more than that of male. And this is the actual table that compares them on the statistical level. And we can see right here standard the C. This is Levene's test of equality of variances. Don't forget that's one of the statistical tests where the assumption that we need to meet. So this calculates the assumption for you, and this gives you the actual, this sector t-test for equality of means gives you the result that you can conclude on. And what you are mostly interested in is is the p-value, which is sig, one-sided or two-sided. We're going to run the interpretation in the next video, but you can guess what the answer would be now, right? Okay, so let's go ahead and check what exactly the answer is from this test. Now that you've seen the result, and now even easy and simple to run this test, but look at the result. I just took this out of the other tables that we have there. This is the table that talks about significant or not. Others are descriptive data or testing assumption. And based on this data, one thing you should look out for is the significant, is the sig column. And from this sig, which is sig two-tail, you can say 0.137, 0.137. That is the significant value. But let's look at the way it's been summarized there. This study found that male participants had statistically not significant average amount spent on clothing per month, which is 88.03 euros, plus or minus, which is the standard deviation at 18.15 euros, lesser than female. Their average spend of male is lesser than female. Female spend 136 euros with a standard deviation of 26.134 euros. The results shows that this p-value is not less than 0.05. It means that it's not significant. It's not statistically significant. This is easy to understand. It's just telling us here that yes, obviously the mean compared shows that one is more than the other, female spend more than male, but based on the variation here, it is not significantly different statistically. So that's the way we conclude. And it's interesting and funny, right? Yes. Even when the values are different and you are thinking, oh, female spend more than male, but you cannot conclude based on this data because statistically it's even proven that it's not significant statistically. So our conclusion is men and women spend equal amount of money on clothing. I know you'll be having some kind of thought, oh, it's not possible, it's not true. But based on the data, so this study found that, if I want to make this conclusion, I'm going to say this study found that male participants had statistically not significant average amount on clothing, spent on clothing every month compared to their female counterpart. And it is based on the observation considered for this study. So that is it. So you have to also be careful of the generalization because it is based on the data. In reality, you can take another sample, you might see that female spend more than male, statistically significant, but you can't find it here now. So this is based on the results considered for this study. Okay. Yes, amazing. And I want you to please subscribe, share, support, drop your review, and thanks. In our previous video, we talked about independent sample t-test. So this one is dependent sample t-test. And what makes it dependent? Let's check it out. The dependent t-test, also called pair samples t-test. Look at the word pair, okay? It compares the mean between two related groups on the same continuous dependent variable. By example, you might get this better. You could use a dependent t-test to understand whether there was a difference in smokers' daily cigarette consumption before and after a 6-week hypnotherapy program. So in that case, it's the same person. Before the hypnotherapy program, you took some data about their cigarette consumption and you administer the program 6 weeks. After that, you collect data about their cigarette consumption again and then compare, is it significantly different from each other. Look at it, the same person is involved in this case, but you're having two different data types, one before, one after. In independent t-test, it is not the same person. We have male, we have female. These are two different people that are independent of each other and you are collecting the same data about them. But here is the same person, but you are only collecting this data at different points in time. One is before a program, the other is after the program. Okay, let's look at the assumptions because assumption is very important to us understand some of these things. First, why assumption? When you choose to analyze your data using a dependent t-test, part of the process involves checking to make sure that the data you want to analyze can actually be analyzed using that particular test. You need to do this because it is only appropriate to use a dependent t-test if your data passes 4 assumptions that are required for a dependent t-test to give you a valid result. And what are the assumptions? Assumption number 1, your dependent variable should be measured at the interval or ratio level. Again and again, it's becoming more and more interesting because we keep referencing interval, ratio, continuous, categorical, which we've talked about at the beginning of this course. In case you missed it, you can always check it out. Examples of variables that meet this criterion include anything you can measure or count, as cited right on this screen. Number 2 is your independent variable, which is the category here now, should consist of 2 categorical data, but they must be related or match peers. Okay, what does all this thing mean is the before and after. It should be the same person. For example, you might have measured 10 individuals' performance in the spelling test. The result of that spelling test is your dependent variable, but you are collecting the data, the results before and after they underwent a new form of computerized teaching method to improve their spelling. So you tested them on that English spelling, assessment before they go through that program. You collected the data for these 10 people. After they went through the program, you test them again. You collected the results. So the same person, this data point is category before and after. So it's peer. It's 2 groups, but those groups are related. They are not independent of each other. They are dependent on each other. And that is what the second assumption is talking about. Number 3, there should be no significant outliers. The impact of outliers, it can make your result invalid. And outliers are simply data point, single data point, that can affect or either significantly higher or significantly lower than the average results. And that way it can make your data really invalid and make you result into the wrong conclusion. Assumption 4, the distribution of the differences in the dependent variable between the 2 related groups should be approximately normally distributed. So when we talk about this requirement, it's more or less checking the variances. How does the variance between before and after, are they normally distributed? So you calculate variance for before, variance after, and check if they are normally distributed, and that way you can meet that assumption. All right, so let's look at a use case to better understand this. A behavioral scientist wants to know whether drinking a single glass of beer affects reaction times. She has 30 participants perform some tasks before and after having a beer and records their reaction times. For each participant, she calculates the average reaction time over task, both before and after the beer. Resulting in this data set, we have a reaction underscore time saved. Can we conclude from this data that a single beer affects reaction time? Yeah. So interesting use case, right? Remember, it's the same person here, but is doing the task before and after. We are checking the reaction before and after, and there's something in between, which is taking a cup of beer. Based on this business use case, we can set up a hypothesis. A single beer does not affect reaction time. The alternative hypothesis is a single beer affects reaction time. So who wins? We're going to test this out. So let's go ahead and test. We then come back and interpret the results. This is yet another interesting use case, and let us test this data. First thing to do is to import our data. Go to File, go to Open, and click on Data, and you see its reaction times. And click on Open. Let's look at the data format. Here we have reaction 1, reaction 2, and we have the ID. So there were 39 records here. And let's look at the variable definition. They are scaled because this is measuring average reaction time before drinking a beer for each of them, and then average reaction time after drinking a beer. So it's the same person that is involved here. Before is measured, after is measured. So you can then see what maybe drinking a beer have effect, and we want to test that. That's what dependent sample test will help you to figure out if the beer is actually the one causing this reaction or not. Okay, then we go back here to analyze the data. You go to Analyze and click on Compare Means and Proportion, and you will see paired sample t-test. That is the dependent. It's called paired sample t-test. Then you click on it. Of course, we need to select the variables we are comparing, so I'm going to use Control key to select both of them and push. So you can see the pair now. Variable 1 is average reaction before, and variable 2 is reaction after. And of course, we can click on this option and set the confidence interval, which we are good with 90. If you need any other thing, you can always check them here. Average of variances to compare, but I'm just going to go with this. It's okay right now, and click on OK. So the result is also simple like others. So we can see the summary statistics for before taking the beer and after taking the beer. This is the mean reaction time, 1165 seconds, and after taking a beer 1288, obviously we can see difference. But can we say this difference is significant or not? So that is what we can conclude on until we look at the Pearson samples test result. But here, Pearson samples correlation, this also calculates correlation between them, and we found out that yes, there is a significant correlation right there. But here's the result. And on this table, we will be interpreting the table soon, but you can see the comparison, the difference between them is 122 seconds, which after taking the beer it increased. And this is the deviation for that. And our calculation p-value, one tail is this and two tail is this. In the next video, we will interpret this. So, let's look up to that and let's check it out. As you can see, it is easy to carry out this test. It is just for us to now interpret this result, which I have extracted one of the most important table here, which is the table you can see right here, because it compares the average reaction time before and after taking a beer. And this is how you can actually report that. One of the things you should look after here is the significance, because that is the value they end up telling you if the test is significant or not. Here it is significant because it is less than 0.05. I can actually interpret this and say we can conclude that there was a statistically significant increase in reaction time after taking a beer from 1,165 seconds to 1,288 seconds. You can see that. So an increment of 122 reaction in seconds, 122 seconds. So, and it's found to be significant. So we go back to our hypothesis and then conclude that therefore we say participants became slower after drinking a single beer. The null hypothesis is rejected, then we are accepting the alternate hypothesis that a single beer affects reaction time. Interesting, right? So you've done with this as well. Don't forget to encourage, by reviewing this course, share with others, and if you are checking it on YouTube, please do like, subscribe, and share. Okay, let's talk about Pearson's product movement correlation. So there are different types of correlation, and this is the most common one that people even often refer to. Anytime they're saying there's correlation, there's no correlation, we often use that term a lot. What exactly is correlation, or this Pearson product movement correlation, often called Pearson's correlation for short, or popularly referred to as correlation? Anytime someone talks about correlation, when it comes to calculation, they might resort to just calculating Pearson moment, but it has some assumptions to determine when to use it or not. But correlation is a measure of the strength and direction of association that exists between two variables measured on at least an interval scale. That is where Pearson movement correlation is relevant. First, interval scale. If the scale is lesser than that, you can't even use Pearson correlation. And what it tested is not the relationship between two variables. It is the strength and direction. So, are these things associated together? How strong is the association and what direction is it? For example, you could use a Pearson's correlation to understand whether there is an association between exam performance and time spent revising. Whether there's an association between depression and length of unemployment and so forth. It doesn't mean one is causing the other. You are not interested in relationship, it's just the strength and the direction of any kind of association that exists between them. And how do we even interpret the results? So let's quickly look at it here. As you can see, there are 4 different diagrams here, and let's look at them. One is when everything sort of converge and it points towards the upward direction. This arrow is like pointing downward, but it's up. When you strike a line, you can have a linear line and everything fall perfectly on the linear line and just shoot up in this direction. In this case, it is perfect positive correlation because both of them are aligned. As one is increasing, the other is increasing. So if it is revision time and exam score, for example, if the way revision time is increasing, the same rate exam score is also increasing, then they have a perfect positive correlation. The second one you have at the right hand side is when it's close to 1. At least it forms a pattern that everything is, as one is increasing, the other is increasing. Everything doesn't have to converge on a line, but you can see a pattern. In that case, they are strong. We can say a strong positive correlation. There are some cases that can be weak or moderate. You can always use different interpretation for that. But when the direction of the relationship is negative, meaning As one is increasing, the other is decreasing. For example, if you look at this one, which is towards the bottom right here, it's a strong negative correlation because on the x-axis the value is increasing, is counting increasing, but on the y-axis is actually reducing. So in that case, it's a negative correlation. It's pointing downward as against pointing upward in the positive correlation. And when everything is so scattered that you could not even plot a linear line to say maybe this is the pattern either going up or coming down, that is a weak or no association or no correlation. That's what you conclude there. Okay. What are the assumptions of Pearson's correlation? Let's go through the assumption. First, why? When you choose to analyze your data using Pearson's correlation, part of the process involves checking to make sure that the data you want to analyze can actually be analyzed using Pearson's correlation. You need to do this because it is only appropriate to use Pearson's correlation if your data passes 4 assumptions that are required for Pearson's correlation to give you a very valid result. And what are the assumptions? Number 1. Your 2 variables should be measured at the interval or ratio level, so they should be continuous. Again, when I talked about continuous data, I explained this in the earlier part of this course and video, so you should check it out. And these are the examples that meet that. Anything you can measure or count, they are numbers. I'm going to also run a test on this. The second assumption is there needs to be a linear relationship. Yeah, before you could even think of doing it, there should be a linear relationship between the 2 variables. Which there are a number of ways to check this, whether a linear relationship exists or not. For example, you can use scattered plot, scatter diagram to check, to just see a visual pattern before you start going ahead to run your Pearson. In situation where you can see no or weak correlation, you might not need to go and test it at all because you already seen from that diagram that, oh, there's nothing between these guys, so why should you go ahead and start testing again? Number 3, there should be no significant outliers. Outliers always, even on the graph you will see, on the scatter chart, scatter plot, you will see any outliers because they're just going to be so far, and it can affect the line you are trying to plot to identify patterns. That can affect your result as well. Outliers are actually any value that are either significantly higher or significantly lower and can impact the average interpretation of your result. So when you remove them and you can do some statistics about data, you get a value, but when you add them, the value you get is significantly different. So you can know that, oh, this value is making this impact, so it's that significant on your model. So that's an outlier. Assumption 4, your variables should be approximately normally distributed. It's just like saying ceteris paribus. There's a way to control and say all things being equal, this is what we're saying, because statistics is not always right. So we need to do our work under assumptions, and normality is just one of those assumptions. Let's talk about this use case, then we'll go ahead and test. First, this is the use case. A policymaker wants to know whether age and net monthly income are related in any way. She asks 30 respondents, resulting in age income data, that is the data, just want to know. And the hypothesis here is, the question here is, does this data render it likely that age and income are related in the research population? So we can then go ahead and form our hypothesis now. Number 1, the null hypothesis is age and income are not related in the research population. But the researcher is interested, so in the alternate hypothesis, which is saying that age and income are related in the research population. So you're just assuming that they are not related, but I'm just interested, are they related? Okay, so now that we have the hypothesis, it is time to run our test. Let's go ahead and run this test. We'll come back and interpret the result. It is time to carry out the correlation analysis, and I'm going to do that by importing data. Go to File, go to Open and Data. You see age income, that is the data that we're interested in. We want to see if both of them relate together. All right, looking at this data, you see we have a total of 30 records, and these are just ID for numbering. Then this is age data, this is income. Both of them are actually scale. So the level of measurement is scale data, and you don't have to do anything with the ID just to identify them. Age in years and net monthly income in euros. So let's go ahead and run our correlation test. By navigating to Analyze, you go to Correlate, and you will see bivariate correlation. Bivariate correlation, that's what you need. Click on it, and then you move both of them into the box. Good. Right here you see several types of correlation coefficient. We have the Spearman, we have the Kendall, and we have the Pearson. What we are dealing with is just Pearson's correlation. Are you interested in one tail? Let's just do two tail. Flag significant correlation. And if you need other things, you can always say, oh, maybe you need to calculate means and standard deviation. Good. And that is okay for me. I'm going to go ahead and click on OK. So the table is simple, yes, but it's really powerful because that's what we need right here. And you can see this is the mean value for age in years, net monthly income. You see the standard deviation, but this is the correlation, and this is the matrix. We're going to interpret this matrix in the next video, but you can see the values are there, and it's also flagged if there is a significant correlation or between both of the variables, age in years and the net monthly income in euros. We are back and we have the results. There are other things you could do to even run further analysis. I'm only interested in this table because this is where we can make that conclusion if there is a significant correlation or not, and also understand the direction of that correlation. Okay, so this table is a symmetric matrix, meaning if you cut it from diagonally from this one and one here, the value you have at this upper side, they are the same thing what you have at the lower side. It's just like a mirror. That's how it is. Even when you have multiple variables, it's always a symmetric matrix. So you can either focus and interpret from the up hand side here or downward side. And let's take an example. This guy is age in years as against net monthly income in euros. And the value here is net monthly income in euros as against age. So it's the same thing. And if we interpret this, the value is 0.730. Correlation ranges from -1 to +1, and the closer it is to 1, the more perfect or strong it is. Then the sign determines if it is positive or negative. In this case, it is positive, and 0.7 is up there, so it's a strong positive correlation. We can take it to be strong and not even moderate, because it's really 0.7 is really strong, by the way. Not really strong, but it's a strong positive correlation. But is it significant? We have to use the significant level to test. If the value here is less than 0.05, we can conclude it is significant. It is, right? Yes, it is. So in this example, we can see that the Pearson correlation coefficient, which is being denoted by a small letter r, is 0.730, and that is statistically significant because p-value is less than 0.05. Okay. In conclusion, we can just write it like this. A Pearson product moment correlation was run to determine the relationship, or better say the association, between age in years and net monthly income in euros. There was a strong positive correlation between age and net monthly income, which was significant, statistically significant. And this is the correlation value, this is number of sample size, and this is the p-value. So it's really less than 0.05. This is 0.0005. The null hypothesis is rejected. We accept the alternative hypothesis. Thank you. We are done with correlation test. In the next, we're going to deal with regression. Amazing, right? If you find this video really helpful, why not consider subscribing and buying my, the full course on Udemy? This way is going to literally encourage me and also support the things I do. There are additional tests that is not covered in this video, and you can see them right here. We have the simple linear regression, interesting multiple linear regression, one-way analysis of variance, correlation analysis. To buy the course, I've put the link in the video description with discount. So definitely there's a discount for you, and I look forward to you supporting the work I do. Thank you.